My name is Alejandro Moreno. I come from the University of Twente in the Netherlands. Where we are doing research on the sensing and shaping of social play behavior in interactive playgrounds. So I will be talking a little bit about what are interactive playgrounds and how are we actually sensing and shaping social play behavior. Before that, a little bit more about me. I think Jenny already mentioned. So I have a PhD from the University of Twente in the Netherlands. Right now I'm a postdoc there at the same university. And my background is computer science. My research more or less lies in the intersection of human-computer interaction, applied computer vision, and interactive play. Now, before beginning, I would like to ask how many here actually have like a social science background? Just raise your hand. In computer science? It's a little mixture, okay. So my hope is that I can bring like a new light or a new perspective on how to do this type of analysis from the perspective of computer science and what we do at the University of Twente. I will be mostly talking about two particular studies. First is shaping children's proxemic behavior in an interactive playground, which was research conducted with Robbie van Delden, Dennis Reisma, Dick Hyland from the University of Twente, and Ronald Popo from the University of Utrecht, and promoting children's prosocial behavior using social robots, which was research conducted with Christina Saga, Vanessa Avers, and some students that did a lot of the lesson. Let's start. Children's play. So I will not go into detail. I think everyone here agrees that children's play is of critical importance for the development of children, right? You have the social, the physical, and the cognitive benefits of play. But I wanted to ask a very quick question. So when I say children's play, what is the first thing that comes to mind when I say children's play? So just throw words around. There's
Games.
no games.
Laughter.
Yes.
Pretending.
Yes.
Fun.
Fun, definitely fun. Playground.
Imagination.
Yes. So more or less something like this, I guess. This is more or less what we have in our minds when I say children's play, which is like a traditional kind of play, outdoor playgrounds. However, nowadays, if someone tells you like this could also be considered children's play, then this is also perfectly fine, right? But then there's a different type of play. It's like digital play. You have computers, mobiles, console gaming, and of course, it's not bad, right? It has its own advantages, its own benefits. But the problem is that certain studies have suggested that because technology has crept into the everyday life of children, it is actually kind of displacing the time that they spend on this type of play, which may lead to more solitary, screen-based kind of play, which is not good for them because they neglect the development of the social and physical aspects. So what we are trying to do is we're trying to design interactive play technology that is able to support active and social play. Now, how to do this? There's two aspects. One is to understand play, so we need to study how children play so that we know what is going on during the play. Now, I think everyone knows here, to study play, normally you go out, record, observe, code, annotate, yada, yada, yada. It's a very long, very cumbersome process. It's quite tedious. So we're wondering, can we do something about this? The other thing is actually shaping play. So since we want to design games that promote physical and physically active social play, then we need to be able to design play technology that is able to support this kind of play and is able to shape the behavior of the children. So this is more or less the model that we use. Basically, you have play, you can sense play behavior, you can analyze play behavior, you can shape play behavior. What we want to do is we want a system that is able to do all of them in a sort kind of loop. So we are able to sense the behavior of the children, then we analyze it, and then we use this information to actually design certain interventions or certain strategies that are able to shape the behavior of the children during the game. Now, it's a loop, so once intervention happens, we are able to again sense if this has worked, and then, okay, it tries to shape again. So the good thing is that we can try a myriad of strategies here, and we can easily see what is the effect of these particular strategies on the behavior of the children. Now to do this, we actually use what are called interactive playgrounds. Basically, interactive playgrounds are areas that combine the digital technology used in interactive games, video games, and try to support the type of play that is commonly associated with traditional play, like playgrounds. So basically, they are technology-enhanced environments that engage children to play in co-located, physically active social play. Now, they can vary in shape and size. Normally, they are room-sized environments where children can just go in and play. So we had to build our own interactive playground, and it doesn't look really nice, okay, but it will look better. Basically, I'm right there trying to set it up in a museum where we did some studies. The system basically consists of 4 Kinects that are placed on the ceiling, facing downwards. With this, we can actually sense anyone who comes into the playground, and we can track their movements while they're in. These are connected to a computer that does all the vision, the tracking. It's connected to a network, which goes to another computer, which does all the game stuff, game logic, game mechanics. And then we have 2 short-throw projectors that display the game on the floor. The size depends on where the ceiling is. In the university, we have a 6x5 meters. The one here at the museum was around 4x4, something 4x3. We have speakers for sounds, and the idea is that it's really like a playground. So ideally, children can just go in and they can start playing. So they don't need to wear any equipment. No one needs to be there actually to tell them to go in. They just walk in, they're tracked, they can start playing. Once they're tired, they can go walk off, and that's it. Now, it's called Interactive Tag Playground because our very first game was a tag game. So that's why it's the clever name. Now, everyone here knows what a tag game is. Game of tag, so like, you're it, right? So we wanted to convert this to digital tag, and I will show a video. These are very small children, so there are some failures here in the tracking, but it will give you a good idea of how it works. Something. I have no idea why it's not playing. Okay, it's a little bit weird. Basically what we do is we track the people in the playground. We display a circle underneath them. We have an orange circle, which means you're the tagger. A blue circle, which means you're the runner. To tag other players, you don't have to physically touch them, but you have to get your circle to touch the other player's circle. Once they touch, then the colors change, and then there's a sound, and then you know that the tag took place. Now, what we are trying also to address is certain breakdowns of play. So when children are playing, for instance, a game of tag, normally because they're running around very quickly, they will forget or they will not notice who the tagger is. And in that case, the game will just stop because no one knows who the tagger is, the game cannot go on. And then they will need to restart. So, for instance, right now the system acts as a referee. So he assigns who the tagger is and he keeps track of who the tagger is. So with this, we're able to solve certain issues with the normal traditional games. Also, because we're able to track the players that are inside, then we can do all sorts of analysis without the need of having someone there to code this information. So, for instance, down here you can see, for instance, the heat maps of position from the players based on their roles. So you can see, for instance, that runners tend to stay in the boundaries of the playground. You have the taggers, which tend to stay in the middle and cut across to try to tag other people. We could measure like the speed at which they move, the distance that they have to each other. Now the actual values are not that important because it changes between the age, the size of the playground, but we can actually find tendencies, for instance, between the different roles, like taggers move faster than runners, the distance that they have to each other, and we are also able to, for instance, analyze the direction in which they're moving in relation to each other. So for instance, taggers tend to run towards runners because they want to tag them, and runners, for instance, try to run away from them because they want to avoid being tagged. So all these analysis can be done automatically by the computer without the need of having someone there to actually, annotate this or make observations, which is very helpful for us because it allows us to do analysis faster. Now, once we knew we could analyze, the behavior of players, and we said, okay, now we have to see if we can use this to shape the behavior of players. So the first study that we did was, well, that's the name of the paper. Basically wanted to see if we could shape or steer, well, we use the word steering, I don't think it's an appropriate word, it's shaping. Social behavior by changing, seeing if we could change the proxemics of the players during the game. So basically we wanted to try to entice children to take more risky behavior in a game of tag. What we did is that near the tagger, some little yellow particles will pop up. And if the runners actually step on them, they will collect them, and their circle will actually change, and it will look nicer. So this, the thing is that these circles actually do nothing for the game. So it just changes your circle, but the outcome of the game is still the same. So basically these are rewards akin to achievements. So they don't make the game easier, but actually they make the game harder because you're taking a risk, you're getting closer to the tagger. So we wanted to see if children would actually take the risk. So can we encourage them or entice them to actually run towards the tagger instead of just running away from them without actually giving them any functional advantage of the game? Now we did 2 different user studies. The first one was at an art gallery workshop where we had over 600 children play this game over 18 days of workshops. The age varied a lot, from 4 to 13 years old. And then we saw how the game worked, what type of things were working, what type of things were not working. And then we did some school visits to our university where they played a refined version of the game. In that case, we had 48 children from 5 to 12 years old, and it was within subject studies. What we did find out was that actually it was possible. So SWOT condition is the one with the particles. It was possible when we did the SWOT condition that we could make children stay closer to each other during the game. So actually they were taking risks to try to approach the tagger instead of just running away and staying away from each other. Also, we could, remember before it was like this, we could change the direction in which they were running most of the time. So now they were actually running towards the tagger instead of just running away from him. Now, some difficulties that we had. Well, first of all, so these are the points of going into the wild, right? So if we had an art gallery that they were organizing workshops. There were several problems because we tried to make it as easy as possible for them to run the game. So basically, they just have to start the computer, turn on the projector, and then in a certain order, and that would be it. And of course, it didn't work always like that. Sometimes it didn't, the right order was not used, or they forgot to turn it on, or things like this. So always things like that can happen when you go into the wild. The space was a little bit limited in respect to what we had in the playground, in the university. Working with children is always difficult. You know, they do whatever they want, whenever they want. So it's also a little bit hard. Because of the art gallery, because the way it was structured, they only had to play a very limited amount of time. So they went in, played, went out. Many different groups. Some children wanted to play again. They couldn't. They started crying, like, you know, I want to play again. I don't want to go to the workshop. And for the school visits as well, once we were coming, actually, it was very chaotic because they would not let us know, for instance, how many children were coming because they didn't know how many had consent forms. And the thing is that everyone has to play. You cannot get a children and then just tell them, oh, you don't have consent form, you don't play. Everyone has to play. So we didn't know how many could play, the gender, the age. So all these things happen. You know, it's really chaos. You have to be aware of these things. Now, something important that, okay, the information that I showed, the analysis, again, no coders, everything was automatically collected by the system. So we are able to analyze this without the use of a coder. Of course, for certain types of studies, this is not possible. It's more like a support for researchers. Now, anyone here knows what machine learning or deep learning is? Not a lot. Okay, so basically, what we did was track, you know, players in the playground. But of course, there are certain limitations. There are certain things that we cannot do with cameras on the top. But nowadays, thanks to deep learning, this is actually changing incredibly fast. So deep learning is basically, you have a lot of data that you have collected. You have a computer that is massively powerful. Then you throw all this data into the computer. It will start analyzing it. It will learn internal representations of the data. And it will learn to recognize certain things. It's more or less that in a nutshell. So some things that you can do actually nowadays is this, and I hope the video plays. No. I don't know why it's playing, but
Have you pressed the play button?
I am.
It's because the mouse for us isn't on the.
Okay, but over here it's.
Oh, it's not.
Okay. Over here it's. So you can see like this skeleton tracking. So you can see the posture of all these people. This is a massively difficult scenario. There's only one RGB camera, like from your laptop or a webcam, and it's incredibly good. See all this amount of people are behind. It still is able to track them relatively accurately. This was just released this year. It's actually a library that you can download. And so we're moving in that direction. That once we have a lot of data, you can actually train these things to, do stuff like that. I actually wanted to show another short video. This probably everyone knows. It's with the same library. So you can see it works relatively well. So now it's probably not even necessary to have like Kinects on the ceiling, have depth information. Now you can probably just get an RGB camera, use this library, and you can get all this information. I know some researchers are now working on getting data from kids, from children. So children interaction, children-parent interaction, to be able to recognize posture, face gestures, fingers, stuff like that. All thanks to deep learning. So it's something that I think that everyone should be aware of going further. So the last study that I want to talk about is the second study we did to shape behavior using social robots. So this is a social robot there. So basically, I showed that with projections you can actually shape behavior. We change proxemics, but you can only go so far using projections, right? Because of affordances. Affordances basically is when you see an object, you kind of know what you can do with this object. That's the affordance of the object. For instance, if you see a chair, I can sit on a chair, then that's the affordance. However, affordances are created by interaction. So an object inherently does not have an affordance. A chair is not necessarily to sit. It's in conjunction with a person. For instance, if I had a tail, a chair is not for sitting. It's very uncomfortable. Then these affordances are really created with interaction. In our case, for instance, we had these circles on the ground. And for instance, you can see this kid was actually stepping on the circle instead of trying to get the circle to touch. Some other children were actually jumping on the circles to avoid being tagged. Here you can see these children don't know what to do with the circles because they're quite young and they're just looking at them. So affordances are very important. So if you want to change social behavior, then you need to look into social affordances, and which are more nuanced, right? Social interactions are very nuanced, or you have a lot of details. So we wanted to see if projections are not enough. What if we put a social robot in it? A social robot has much more social affordance, many more mechanics that you can use. So when I say social robots, maybe some people are really thinking some extravagant things. So something like this, maybe. This is a social robot as well.
No, you were still active. I heard a sound of distress. What seems to be the trouble? Oh, I just stubbed my toe a little. I'm fine. On a scale of 1 to 10.
Mind meter.
Your pain. 0? I'm okay, really. Thanks. You treat now. Does it hurt when I touch it?
Well, the important thing is that we're, of course, not there yet, but it's not necessary to be there. So, you can, this for instance, this is just cleaning robot in the street. I love your robot. So it's not necessary to have these very complex, social robots. Just the fact that they're embodied actually helps for the social interaction with kids. Now, to test this, to test if we could actually leverage these social affordances by the robot to shape behavior, we implemented a game called Hatchimal. It's basically a cooperative game between two kids and a robot. And basically, they had to hatch eggs that would appear on the playground. So these are the eggs. Once a kid stood on one egg, it will start to hatch, and at some point, a bird will come out. There was a cat roaming around the playground, will try to destroy the egg. So the children had to actually prevent the cat from destroying them. And to encourage team play and cooperation, when a kid stood on one of the eggs, then a line would draw towards another egg. And if another kid stood on that egg, then the speed at which the eggs would hatch was doubled. And also another line would show to a third egg. If a third player stood on it, then you will have these really fancy particles that would show up, but it will have no functional advantage. So only 2 players needed to actually cooperate to have these functional advantages towards the game. We wanted to see if we could use a robot to actually promote this coordination, cooperation, and social behavior. So the thing that we did is that this one. So what we did is that halfway through the game, and at the end of the game, there was an event where the robot tried to hatch an egg, and he would need help. So this line will be broken. So there was no possibility of doing team hatching. So if a kid stood on this, it would fix the line, and then you could do team hatching again. The robot could hatch it on its own, so it was not mandatory for the kids to do it. But if they wanted to cooperate with the robot, they will need to fix it before start hatching together. So we implemented 2 very simple behavioral repertoires for the robot based on motion, lights, and sound. Lights and sound, yeah. So in the cooperative condition, basically the robot would actively seek the eggs that were connected to the children and try to hatch together with them. If he managed to do it, he would show happiness in lights and sound. And if he didn't manage to do it, he would exhibit sadness. And in the selfish condition, he would actively go for the eggs that were not connected. So he would just go to them, try to hatch them on his own. If he managed to hatch on his own, he would show happiness. If a kid tried to hatch with him, he would show sadness. So he was trying to just play on his own independently. We had forcing children play with the robot, 8 to 12 years old. We did a between subject study. And our expectations was that for the cooperative robot, then children would actually try to help the robot more and try to play with him more, which is actually what we found. So once we did the results, then we saw that the rate of team hatching was significantly higher for the cooperative robot, which makes sense because the robot was also taking part of that. But more importantly, when the robot needed help, in the cooperative condition, the children would actually help the robot so they could hatch together. But when they were playing with a selfish robot, they will ignore the robot and then hatch eggs on their own. So by changing the behavior of the robot, and with the game mechanics, we could actually encourage the children to engage in prosocial reciprocity, things like this. First, we had some difficulties, are similar to before. The main one was that the robot was controlled by a user, so it was a Wizard of Oz setup. Ideally, we would like to have an autonomous robot, but this is quite difficult, but we're getting there as well. So, opportunities or take-home messages. Basically, technology can help us study children's play, and as I mentioned, it's getting better very fast. So I think everyone should really get on with this. Really read about what types of things are there. So what Ellen was saying, like technology can really help us speed up the way in which we analyze and process data. And the second one is that play technology can be used as a vehicle to shape children's behavior. Of course, for different tasks, you will need different technology, or the affordances. And this actually, I think, something very important that we're actually not addressing. In the HCI community, and social robotics especially, normally we evaluate these systems with several children, but it's more like 1 or 2 sessions. We don't really do longitudinal studies. So we don't know, for instance, if this kind of behavior actually is able to translate to real life. And a lot of people are actually doing a lot of they're doing robot tutors to teach handwriting, math, science, also children with autism to help them, encourage them to ask for help, things like this. But it's all important to see if it's not just with the robot, but if this actually translates to other people, which is something very important. I think people that are in social sciences could actually help with this. So that is the end of my talk. Thank you very much.
Any questions for Ali?
Wondering how sustainable it is in terms of like cost and what, because it seems like this requires a lot of equipment. So in a poorer community, how would this be able to work, or would it be able to work at all?
Yeah, so I think for the interactive playground, it's actually, I think it's getting better. I think at the beginning when we bought the equipment, we had like really fancy projectors, really fancy computers, because we wanted to set it up in the lab and we wanted it to work. This was like 6 years ago. Like nowadays, for instance, I have a friend, so Robbie Van Delden, the colleague that I was working with, he actually just recently installed this in a hospital. And then he just bought some, run-of-the-mill projectors. He just took a computer that was my computer, so it was again 6 years old computer, not very powerful, and it's working there. So I think it's actually getting better. And as I mentioned, like right now you don't even need Kinects. You can just get an RGB camera, like a webcam, and you can actually make. So I think slowly it's getting better. The robot that we showed was basically a base, and then the rest was built up with like sticks and paper and stuff. So I think it will become much more scalable in the future. I don't think it's so outlandish even right now.
Even with the Kinects, it's just on even with the Kinects, you can buy Kinects very cheaply nowadays.
Yeah.
They cost like £5
Maybe. I don't know. I guess RGB cameras are also very cheap. So the good thing with the Kinect is, okay, you have the depth information, so that helps a lot. But I think in the way that deep learning is progressing, I don't think you will even need that. Maybe for some other stuff. But yeah, I mean, I think it's scalable in the near future.
Question here.
Hi, it's really interesting work. Just to go back to kind of the slides that you started with the kind of just the pictures of the children in the playground, and then you jumped to the pictures of the children playing Minecraft. I just wonder kind of what are your thoughts on kind of what, and you said kind of we want to integrate the two. Like, what are your thoughts on kind of what are the best aspects of digital play that we want to integrate into physical play? Because that was actually quite different. That's the question you started with. It was quite different to the question you ended up with, which was how can we use this to manipulate how children play physically?
Well, manipulate is a strong word, but yes. So I think that digital games have certain elements that really attract children, right? They're able to keep them engaged for a very long time. So you have children that can play video games for hours and hours. So I think integrating this type of game, so this is achieved through very clever game mechanics. So you have to have a game that is interesting for the kids, that is able to really get their attention and keep it. So the idea is to try to take this aspects, the aspects that are able to cause this, and mix it with the type of, a certain environment where they really have to move around, they really have to interact with each other, so that you can actually get them, together, playing together for very long periods of time. So I would not know like what specifics are the strategies, because that would probably depend on which type of game you want to implement. But that's more or less what we want to do, and that's why you need to study play. So you try to do something, so you plan an intervention, you try it out, it didn't work, okay, let's try something else. So that's the advantage of having this, for instance, this system, that we can just try systematically different types of interventions and then see how it affects, whether it affects, maybe it doesn't do anything. So yeah, something like that.
Final question for Ale, right at the back.
I have a question about your algorithms, actually. It might be a bit detailed, but I was wondering what's the maximum level of complexity that your algorithms can do? You don't need a coder to code the play behavior. You use these algorithms to create the heat maps and so. What's the most complex thing?
So actually what I showed here, it's actually not that complicated. I think the tracking is the most difficult thing from the whole process. So you have to implement a system that is able to track them. But once you have that, the rest is quite easy. The system just gets the X and Y positions of every player. And then you know the roles of the players because they're playing the game. So you know whoever has the orange is a tagger, whoever has the blue is a runner. So if you have that information, for instance, building the heat map, it's just counting how many frames or how much time they were here, and then you can build the heat map. That's extremely straightforward. And then for the speed, I think all of it is quite easy. So for this type of analysis, if you want to do like more complex analysis, for instance, like I was saying, like if you really want to analyze very fine detail, like fine-grained social interactions, then what we have right now is we cannot do that. But for instance, with this, for instance, the library that I was showing, that one is really able to like get the skeletons. I saw that, for instance, they can also get face gestures. They can really get the fingers from. So once you have that, that's like you can really do so much more. But the system that we have right now is able to like a very coarse analysis of behavior, which is useful for games. So for what we do, this is enough. Of course, we want to move forward. We want to be able to detect, for instance, when children are cheating, or stuff like that, right? And then try to do something with the game to not necessarily prevent that they cheat, but do something about it.
Okay, thank you very much, Alan.